Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, so welcome to Dynamics ECS 429. So today I'm going to explain to you about the theory about dynamics. So basically, you have to bear in mind, for your information, let's assume every material and structure in the world vibrates. Okay, it vibrates with a preferred natural frequency, but however sometimes the amplitude of the vibration is so small that you cannot really able to feel it. Okay, for example, if you look at a bridge, you see the bridge bridge, the bridge is standing very still, and however actually the bridge is actually vibrating. Okay, it's just that the amplitude of the vibration is very small, and sometimes we cannot even feel it. Okay, so it's not only structures that vibrates, everything that has a mass vibrates. Okay, even the molecules in the water vibrates. Okay. Okay, and okay, all right. So next slide. So what is vibration? Okay, in the context of dynamics, a vibration is the oscillating motion of a body or a system of connected bodies displaced from a position of equilibrium. Okay, what are the types of vibration? There are free vibration occurs when the motion is maintained by gravitational or elastic restoring force, such as swinging motion of a pendulum or the vibration of an elastic rod. Okay, and then we have force vibration. It is caused by an external, periodic, or intermittent force applied to system. When you apply a force to this system, we call it force vibration. Okay, and then we have undamped and damped vibration. So what does undamped and damped vibration means? Okay, an undamped vibration excludes, does not involve any frictional effects in the analysis. But when a damped vibration, it is include frictional force are present. So as we know and as we are aware, every mass will have an external force present. So we can say that the motion of the vibration of a body usually is assumed as a damp vibration. Okay, all right. Now I'm going to explain to you an example of an undamped vibration. Okay, okay. So I'm sure you can see my screen now. Okay, just give me a second. Okay, hold on. Okay, all right. Now, well, I'm going to explain to you the most simplest type of vibrating motion that is an undamped free vibration. Yeah, example of an undamped free vibration. Okay, a very good example and the simplest example that I can give you for undamped free vibration is represented by a block. So here we have a block shown in the diagram here, as you can see, and represented by a block with some springs. Okay, okay. So this spring has a stiffness K, and this is X. Okay, all right. So this is what you call the equilibrium position. Okay, now. So the vibrating motion occurs when the block is released from a displaced position X. So what will happen is the spring will pull the block, okay, and the block will what will happen will attain a certain velocity such that it will move out of this equilibrium position, okay, and what will happen to it it will move out from this equilibrium position. Let's say this equilibrium position x is equal to 0. It will move out from this position and it will oscillate back and forth. But however, it will oscillate back and forth when has a smooth surface. So let's assume the surface is very, very smooth. What will happen? It will oscillate back and forth and it will non-stop. It will move back and forth, back and forth, and back and forth non-stop. Okay, so the time dependent path of the motion of this block can be determined by applying the motion to the block where it is displaced in an x position. So let's say this, so what we do, we draw a free body diagram. So this block here has of course a normal force, and the block of course will have a weight, and then we have the spring stiffness force, which is Ks. Okay, so this is represented in this free body diagram here. So the elastic restoring force is F equals to Ks. This is what we call the elastic restoring force. Okay, is always directed towards the equilibrium position. Okay, whereas the acceleration A is assumed to act in the direction uh, of positive displacement. Okay, so since acceleration equals to d2x over dt squared, we can also assume the direction to be x double dot. Okay, all right. Now, if we use the Newton's second law equation, summation fx equals to ma, and this is the direction of the arrow is positive in that direction, then we will get negative kx equals to mx double dot. Now, you can see that the acceleration is proportional to the block's displacement. Okay, so when it is proportional, what we can do is we can describe this as a harmonic motion. So this is what we call actually a simple harmonic motion. Okay, all right. So we can actually rearrange the formula into a standard form, which is x double dot plus the natural frequency squared multiplied by x equal to 0. So we've used this formula before in our previous example, where we use that omega symbol, and it's actually this symbol or wn or omega n is actually the symbol for the natural frequency. Okay, okay, and then the constant natural frequency is reported to be in the units of radian per second. Okay, and this natural frequency in this case is also equals to the square root of k over m. Okay, all right. Now, there are, okay, hold on. Okay, now, what else? Okay, now. Now I'm going to go to equation. I'm going to go into another equation. Um, when the equation is differential with a constant coefficient, it can the x which is the amplitude can also be represented as a sin uh, natural. Oops. Hmm. Oops. Okay, hold on. A sin the natural frequency time multiply by time, B cos natural frequency over time. You can refer this equation, derivation equation in the textbook, but I'm not going to focus it to the equation now. Oops. What happened? Okay. All right. I'm not going to focus this equation now. Am I still recording? Let me see. Okay, it's still recording. Okay. All right. Then this equation, when you derive it more, it will also be equal to xc sin natural frequency multiplied by t plus phi. Okay. However, these two equations, we're not going to go into detail. You can refer to your textbook or your notes to understand it. But what I want to focus here is the formula for the time, the one cycle. Okay. So here we have a diagram. Okay, so I'm going to draw you a complete one cycle. So if it's a complete one cycle, this is a one complete one cycle is from here to here. So this is what you call one cycle, which is equal to 2 pi equals to the natural frequency multiplied by tau. Okay, one cycle in time. Okay, one cycle in time is t equals to tau. Okay, this is what you call tau. Okay, so when the natural frequency multiplied by tau, it will equals to 2 pi. So then we can find the time of in one cycle, calculate the time for it to oscillate in one cycle is equal to the tau equals to 2 pi divided by natural frequency. Okay, so this is a formula which is very common to you, and you have used it in order to calculate um, the topic vibration. Okay, now the natural period. Okay, the natural period uh, 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 tau can also be represented by this formula, which is 2 pi equals to multiplied by the square root of m over k. Okay, all right, this formula is also familiar for you. And then finally, you find the natural frequency. You can find the frequency by using the formula F equals to 1 over tau. So this is the formula for the frequency. So it is also equals to the natural period divided by 2 pi. So the frequency we can say is also equals to 1 over 2 pi equals to k over m. Okay, so these are some important formulas that you need to know. Okay, now there is another two formulas that you need to know in topic vibration, which is the maximum velocity. If they ask you to calculate what is the maximum velocity, the maximum velocity is x, which is the amplitude multiplied by the natural frequency. And if they ask you to calculate what is the maximum acceleration, it will be the x, which is at the amplitude multiplied by the natural frequency squared. Okay, now I have just one simple example that uses that uses oops, oh no, my Microsoft whiteboard is missing. Let's go back here. Okay. Okay, it's back. Okay. I don't know what happened today. Okay, for your information, I'm sorry for the delay of this video. This is actually the third time I'm recording this. I hope this third time that I'm recording it, no this internet disruption will happen. The first time I recorded it halfway, my laptop battery went out. The second time I recorded it, there was no internet. Now this is my third time. please make dua that there's no problem and I can send to you this video again. Okay, now, okay, so let's do this question together. Just one question that uses these two formulas, okay? Because these are two new formulas that I want to introduce to you. A particle moves in a simple, okay, copy this question, a simple harmonic motion, okay? Knowing that the maximum, okay, velocity is 200 millimeters per second and the maximum acceleration is 4 meter per second squared. The question is the determine the determine the amplitude. Okay, when it asks you to find the amplitude, it means it wants the value in meters or millimeters, yeah, the displacement, yeah, and frequency of motion. Okay, now, so is given the velocity, we change the units, it will be 0.2 meter per second. The acceleration is 4 meter per second squared. So what it wants us to find now is the amplitude. It means we need to find x and we need to find the frequency. Okay, so to find x, let's use the formula. V equals to x multiplied by natural frequency. So that will be 0.2 equals to x natural frequency. A acceleration equals to x natural frequency squared. It will be equals to 4 x, which is the amplitude, multiplied by the natural frequency. Okay, now, so in order to simplify this so that we can get the natural frequency, is very simple. We have this equation 1, equation 2. We divide equation 2 and we divide the equation. Okay, divide. So what we will get will be, we will get 4 over 0.2 and we will be remained with the natural frequency. So here we can get the natural frequency as 20 radians per second. So then what all we need to do is just put it back into the equation. So what we will get is we can get x equals to 0. X will be 0.2 divided by 20 and you will get 0.01 meters, which will equal to 10 millimeters. So this is the answer for the amplitude. Okay, the amplitude is also similar like a displacement value. Okay, so if they ask you to find the displacement value, you can simply use this formula. Next, the other thing is we need to find the natural frequency. So let's have a look at the formula. So we can use the formula here, which is very simple, to find the natural frequency. Okay, so we can find f equals to the natural frequency divided by 2 pi. So it asks us to find the frequency. So we have the natural frequency, which is 20, and then divided by 2 pi. So our answer will be 3.18 hertz. Okay, all right. So this is it, which is important in topic vibration. Okay, all right. So let's just have a browse through into our slide that we have. Okay, so basically this slide is already given to you. I would expect for you to go through it. Okay, so all the notes lecture slide, please go through. So this is our learning outcome. Solve the free vibration, simple harmonic motion, apply Newton's second law, okay, to determine the equation of motion, and then principle of conservation energy of period of vibration. Okay, so this is an example of a person running at space. There's might cause unwanted vibration. Okay, so that's why I have installed a treadmill. Okay, So this is the definition of mechanical vibration. Okay, so all of this you can read and refer. Okay, so this is an example of a simple harmonic motion. All this, okay. All right, this one, uh, all these are things that you can have a look into your notes. Okay, all right. I'm just gonna skip all this. Okay, here there those are the two important equations that I've highlighted to you. If they ask you to calculate the maximum velocity, it will be equal to this x multiplied by natural frequency, and if they ask you to calculate the maximum acceleration, it will be equals to x multiplied by the natural frequency squared. Okay, here are some examples of previous final exam questions. Okay, all right, okay. Here, there is a concept question here. The amplitude of the vibrating system is shown to the right. Which of the following statement is true? So C is the answer. The maximum displacement occurs when the acceleration amplitude is a minimum. Okay. All right. Here, there is a sample problem 19.1 in your textbook that you can try. Okay. See, it uses the formula that I've highlighted to you, which is the maximum velocity and maximum acceleration. Okay, all right, I think that's all. Okay, I won't be highlighting, you can refer this. So I just want to browse through as quickly as possible and make this video very short for you, so I don't want you to look too long. But however, I wish you good luck for your assignment tonight. You have 15 objective questions. I hope you get all of the questions 100% correct. Okay, I'll make dua for you. So all the best and good luck. Okay, so I will stop my video now. Okay, thank you and sorry for the delay of this video. Okay, bye.